Welcome to a lesson with Dr. Powell. In this video, we will look at the intuition behind the Chinese remainder theorem and solving systems of congruences. Suppose that we have z mod 5z cross z mod 7z and z mod 35z. Compare them. They both have 35 elements because we're taking ordered pairs in this mod and this. We have 5 elements in z mod 5z and 7 elements in z mod 7z. Also realize that the cosets of 35z, like shifts of 35z is a subgroup of z, shifts of it are actually contained, like a plus 35z is contained in a coset of 5z, namely a plus 5z. A plus 35z is contained in a coset of 7z, a plus 7z. This is nice because this coset containment actually allows us to have a nested fiber box diagrams. Nested fiber box diagrams allows us to say that there is a function h which makes this diagram commute right here. So fibers of if a fiber of this function would be like 1 plus 5z here, and a fiber of the top function right here be 1 plus 35z. Notice 1 plus 35z is completely contained in this fiber, and that containment allows us to say 1 plus 35z should go to 1 plus 5z down here, whatever fiber it's completely contained in. That containment allows us to have a well-defined map, z mod 35z to z mod 5z. Now we can do that in both components, not only in so here this bar right here is referring to 35z. This single bar right here is representing mod 5z, and squiggle, let's suppose that means z mod 7z. So we have a well-defined function that goes this way. Let's see, that goes from x bar, or from x thick bar to x thin bar, as well as x thick bar to x squiggle. So basically, for mod 35z, you can pair these two well-defined functions or maps together. So z mod 35z will map to z mod 5z, comma z mod 7z in this way, just with throwing a bar over things where this x bar will go to that. This should be a well-defined function, is what we get from that. So we have this well-defined function, and we know that the size of the domain is the same as the size of the codomain. But we don't know if everything's hit yet. That's where the extended Euclidean algorithm comes in handy. So let's look at 5 and 7. Apply the extended Euclidean algorithm to it using our different quotients, -1 and -2, in a matrix, getting the bottom row of the matrix within 1, -2, just picking out this bottom row, matrix multiplying it to it, and you end up getting -2, 3 times 7, 5 is equal to 1. All right, the GCD of 7 and 5 is 1, and we're going to be using that idea that the greatest common factor of 7, 5 is 1. This will work because of it. So we want to show that this map's actually an isomorphism, and all we really have to do is show it's a surjection, because the domain and the codomain have the same size. If it has a surjection, then it's going to be injective as well, and thus it'll be an isomorphism. So in showing that, right here, we have this computation is equal to 1, -2 times 7 plus 3 times 5. Now look at this -14 and 15. We're going to look at those for a minute here and see kind of what they give us. In particular, think about -14. Mod 5, it's 1, and mod 7, it's 0. 15, mod 5 is 0, and mod 7 is 1. So you end up kind of getting these things, this kind of 1, 0, 0, 1 thing, just from the -14, 15. See how that helps us here. So we have this function, all right, and it sends x thick bar to that, -14 to that, and 15 to that, all right. Now let's choose any so we want to show that we have a surjection. Let's choose any A bar B squiggle in the codomain, and notice that something that it's actually sent to. By decomposing it this way and throwing it back, knowing we have a preimage of 1 bar 0 squiggle and a preimage of 0 bar 1 squiggle, we actually find something that maps to it. In other words, it is surjective. So if we were to draw a fiber box diagram, we'd get that the fiber over A bar B squiggle is non-empty. So every fiber box is non-empty, it's surjective, so we end up getting H is bijective. And also because we have that these maps component-wise are homomorphisms, Z-module homomorphisms, we actually get, we can actually go, and it's bijective, then the inverse function is also preserves the structure necessary to be a Z-module isomorphism. Okay, so the behavior of the inverse function, you can take a look, you can kind of think, okay, so if we have A bar B squiggle, it's going to be sent to simply to A times negative 14. So just what we were talking about here, A, B, and negative 14, 15. We could think of this as being a map between free Z modules that have no modding, like Z cross Z to Z, Z2 to Z. And in doing so, you can kind of think of there being a matrix map thing, like negative 14 is like the image of E1, and 15 is like the image of 0, 1. Kind of a modded version of those. This helps us think about a system of equations. So if we want to solve a congruence, or system of congruences, like x congruent to 2 mod 5, x congruent to 4 mod 5, think about this as being like 2 bar 4 squiggle, and apply this inverse function, or the inverse isomorphism that we had going back the other way, and we end up getting a number 32. Notice that, but wait a minute, if we take 32 and we work it this way, we get, working the other way, so 32 thick bar, we're going to get 32 thin bar, 32 squiggle is going to be equal to 4 squiggle 2 bar. Hey, that's exactly what we wanted. That's how we solve it. The 32 actually solves this congruence. 32 works. But remember where 32 lives. It lives mod 35. So all the solutions happen mod 35. So 32 thick bar gives all the solutions. But not only is this an isomorphism for Z modules, it's also a ring isomorphism, meaning it preserves the multiplication structure as well. And you can kind of think about how, because these different bars themselves split across the multiplication, they themselves preserve multiplication in each component here, and so you can kind of split up this computation component-wise and see that A bar A squiggle is actually the image H of A, and B bar B squiggle is the image H of B. So we can actually see that multiplication is preserved by this map. It is a ring. It's actually a ring isomorphism, both of them. So we have the Chinese remainder theorem. It allows us to, in particular, solve systems of congruences like this. Thanks for watching.